G'day, Mr. Hannay here, continuing in the series on differentiation. For today, we've been doing lots of work actually on differentiation, but we haven't stopped to ask the question of when is differentiation allowed? When is it not allowed? And we've seen that it is allowed for any sort of polynomial, so it's allowed for a function of x that is, say, x squared, or f of x being 5, x to the power 4, so plus 3x squared, who knows, okay? Any polynomial is allowed to be differentiated. And so are a bunch of other functions, so things like logarithms, things like square root functions, lots of things can actually be differentiated. But not everything can. So when is differentiation allowed? Well, essentially the answer is differentiation is allowed whenever it's allowed. It's allowed if f of x exists. If f of x actually exists at the point you're talking about. If it exists at x, it also must be continuous. And I'll talk about what that means, continuous at x. And lastly, it must also be, and it also must be smooth at x. Okay. Now, a fancy way of summing up all those things is to say that the limit as h approaches 0 of a function of x plus h, take away the function of x over h, if that limit exists. Because if that limit exists, that means that our function it exists at x, it means it's continuous, and it means it's smooth. Okay, and we're going to go through some examples of when f of x doesn't exist, of where it's not continuous, and where it's not smooth. And we'll think about each one in turn. So first, we're going to think about when f of x exists and when it doesn't exist. So over here, we've got a graph of y equals x. Except, there's a little hole. There's a little hole here right at this point 1, 1. That's one point where it doesn't exist. So here, if I wanted to find, for this graph here, if I wanted to find f dash of x, well, my function of x is just x, so h dash of x is just 1. Except, if I wanted to find h dash of 1 itself, because that point doesn't exist, it's a hole. Okay, so that is undefined. Undefined. Okay, in other words, h dash of x equals 1 for all the real numbers except for 1. Okay, it's not allowed at 1 because the function doesn't exist there. Okay, so we're talking here about f of x must exist at the point that you want to differentiate at. Maybe I should call this point a at a, which is the point here. So in this case, a equals 1 in this case. Okay, check out this next example. This is where our function is the square root of x. Now usually, hopefully you would know actually that we can write the square root like this. The square root function is just x to the power of a half. So therefore we can differentiate it. H dash of x equals a half. And then taking 1 away from a half gives negative a half. So you could also write that like this. Half times 1 over square root of x. Like that. If you wanted to. So there, the derivative does exist in this case. Except check out this whole region here. This whole region is empty. So here f of x does not exist. Not exist. Okay, so this function here, it only works for when x is actually a positive number, over in this region. So it's, yeah, the function stops being defined over in that negative region. Okay, so there's a few cases of when f of x does not exist. Okay, next up is this idea of smoothness. Okay, so this idea here, x must be smooth. So let me write this down. F of x must be smooth. Okay, now we've actually already looked at smoothness. What we said for smoothness is that the gradient approaching from the left, so we said the left-hand side gradient must be equal to the right-hand side gradient for something to be smooth. So in other words, the left-hand side f dash of our point that we're talking about, point A, must be equal to the right-hand side f dash of A. Okay, the gradients on either side must match. Now, check this example here out. This is actually a hybrid function where the function is equal to x in the positive region, so that's when x is greater than or equal to 0, but the function's equal to negative x if x is a negative number, less than 0. So you can see here, this is the bit where you have y equals a negative x, and this is the bit over here where y equals x. Now you can see that coming from this angle over here, we've got a gradient of -1, but coming from the other side, we've got a gradient of 1. And so right here, where those 2 points meet, the left-hand side gradient is not equal to the right-hand side gradient, so it is not smooth. So in this case, you cannot differentiate this thing at that point. It's not allowed to be differentiated at that not smooth point. Okay, so there's one about smoothness. Okay, let's have a look at the next thing. Okay, that one's a bit weird. I might actually come back to that one. Okay, so the next thing we want to talk about is something being continuous. Okay, so f of x, our function, must be continuous. Continuous at our point A that we want to talk about. So, well, what does continuous mean? Well, it means a few things. Like, firstly, for something to be continuous, it means that the point must actually exist itself. Okay, so you can tell straight away that it's not continuous here because it's not joined up, if you like. Or going back to the first example, this is not continuous because there's a point missing here. Okay, so it doesn't continue through. So that means it's not continuous at that point. Also, for something to be continuous, the limit must exist. Okay, so the limit as x gets closer to your point A that we're talking about, that limit must exist. So of f of x, it must exist. And for a limit to exist, what that means is this limit, if you approach from the negative side, so as we go this way, must be the same as the limit as you go this way. Now let me give you some more explanation of what that really means. So a way of writing it is the limit as you're coming from x from the negative side and as it approaches a of our function, it must be equal to the limit as x comes from the right hand side, the positive side, as that approaches a of f of x. Okay, so what this means is, what does the function approach, what value does the function approach, get close to, when x gets really close to the point we're looking at? So here for this example, our a point is 0. Okay, it's this point here that we're interested in, where you can see that there's an asymptote along here. Well, from the negative side, you can see that that this graph keeps getting smaller and smaller. It goes down all the way to sort of negative infinity. So the limit of f of x as it approaches 0 is going to be negative infinity. So on this side, our limit is negative infinity. But on this side, as x keeps getting closer and closer to 0 from this side, the graph goes up and up and up. F of x is approaching, it's getting larger and larger, it's approaching infinity, positive infinity. Okay, now, so on the left-hand side, the left-hand limit is negative infinity. The right-hand limit is infinity. Okay, so these limits don't match, so we can say the limit does not exist. Does not exist. Limit does not exist, so therefore it is not continuous. Okay, so this is a bit of a fancy way of saying that it's not continuous. Okay, another thing that you need to say for it to be continuous is the limit. These limits, they must not only equal each other, but these limits, they must also equal the function at that point A. Okay? So they must also be equal to the function at that specific point. So perhaps I'll give you an example where this actually is true. Okay? An example of a graph where it is continuous. Let's do a fairly easy equation. Let's do bad axes. X, Y. Let's just do this graph here of y equals x squared. Okay, and let's think about this point here. So our A point is going to be 1, and you can tell that. So this is our function. Function of x is x squared. So our limit coming from the left-hand side, well, if we put 1 in at x squared, this value is 1. So if we come from the left, we're getting closer and closer to 1. So the limit as x from the negative side approaches 1 of our function, which is f of x squared, by the way, is equal to 1. And our limit as x approaches from the positive side approaches 1. In other words, as it comes down here, it's also getting close to that point of f of x is also getting to 1. So the limit does exist. Limit does exist, which is good. And also, the limit at that point is also equal to the function at that point. If we do the function of 1, that's 1 squared, which equals 1. Okay, so this limit does equal 1. Okay, so all of that, put it together, it means that f of x is continuous. Okay, in fact, it's everywhere continuous. Everywhere it is continuous. Okay, not only that, but it's also smooth. Okay, so it's continuous and it's smooth and it exists, so it is definitely able to be differentiated. Now, just to show you one more curveball case, this one over here, if you look at the point 0, as you come in from this side, it looks like the gradient is getting the same, and on this side, so the gradient's becoming infinite right here, and the gradient's becoming infinite here, and it's continuous and it's smooth, but it's not differentiable at x equals 0 because if you put a tangent line in, you see that the gradient's actually negative. So this is, the gradient is infinite. In other words, the gradient is undefined. So an undefined gradient means that it's not differentiable. So this is like a super weird case. Weird case, infinite gradient means not differentiable as well. Not differentiable. It's not differentiable. Okay, interesting. Alright, as that's basically the basics of when things are able to be differentiated, when they're not. So let's just have a quick recap. Things are allowed to be differentiated if they exist at the point you're talking about, if they're continuous, which means the limits from both sides equal each other, and it's smooth, so that means the gradients as you approach from each side are the same. Okay, so exists, continuous is all about limits from both sides are the same. Both sides equal. And smoothness, all about gradients from both sides. Both sides equal. There we go, and it's pretty easy to spot if you actually have a graph there. Now, I want to do one very last thing, which is just about limits. Okay, so thinking a little bit more about limits, because we mentioned the very last thing we talked about was when the limit from the left-hand side, like the limit as say like x approaches from the negative side, let's say it approaches 0 of some function. Is there ever a case, you might be wondering, is there ever a case where the limit from the left-hand side is the same as the limit from the right-hand side? Is there ever a case where this is true and it doesn't equal, these limits don't equal f of 0, like f of that point there? Is there ever a case where this is true? And I thought I'd just show you one, just so you know that yes, it can happen. So here's one here, one that you've seen before, is a truncus. Okay, so this has got its equation, f of x equals 1 on x squared. So you notice that as we approach from this side, the gradient's becoming larger and larger and larger. It's becoming infinite. So the gradient on this side, f dash of x, on that side is becoming infinite. And over here, f dash of x is becoming infinite over there too. By the way, this is the limit, I should say. Limit x plus approaches 0. And this is the limit x minus approaches 0. Okay, they're both infinite, they're the same, but the function at 0 is undefined. Undefined, because you can't divide by 0. So that's undefined. So here's a case, here's an example of where you can have the left and right hand side limits, but non-existence. Okay, it doesn't exist, but the limits do equal. And that's why we need all three of these conditions. Okay, we need the existence one, we need the limits one, and we need the smoothness one about gradients. Okay, hopefully that has been very useful for you. And I'll see you later for the last video in this section.